Okay, but before we do this, I would like to talk with you quickly about the quotient. And you probably know how to work with the quotients, or sometimes it is called the quotients. But for me, again, it's important, the concept. So during the lectures, we're going to talk about some really simple things, but the main idea is not only important is understand these things, these techniques and these definitions, but also to understand the concept, how we are working on the top of the rules. So we discussed about the numbers last time. We said that there is an integer, then there is the rational number, irrational number, the real number, and so on. And if you remember, we defined the rational number as the ratio of the two numbers, right? For example, n divided to the m. So at the same time, this kind of numbers are also called the quotients or quotients. And there are certain operations with the quotients, like how we can multiply the two quotients and how we can add the two quotients. But before we do these two operations, I would like to ask you whether you know how we call the upper part and the lower part of the quotients. Do you know how we call the upper part of the quotients in English?
Yes.
How we call this upper part?
Numerator and denominator.
Okay. In Russian, we call this числитель. In Uzbek, we call this as surat, right? Oh, by the way, I need to know that starting today, I would like to, do you have any suggestions on how we can track the attendance, class attendance?
Yes. Maybe we should write our ID numbers on the chat.
No. We should, I mean, we are engineers. We need to think about like more rigid, more better way, more intellectual way, right? So, writing ideas is like super easy to cheat, right? So some of you can write like a couple of ideas and that's it. So I figure out the method. It's like you need to log into the Zoom with your Akva University email account. So whenever you go to the Zoom, you need to log in with your Akva University mail account. And if you stay longer than 30 minutes, then I can count you as attended. So what I'm going to do is I'm going to download the log files of the Zoom, and then I'm going to post-process this using some scripts. It will identify you by your ID, by your university mail account, and track your attendance like this. I think it is good. Since we're engineers, we need to think about more sophisticated ways of tracking attendance, right? But
yes.
Yeah, okay. So if you didn't log in with your Akva University mail account, so I would like to kindly ask you to go out and then to come in again one more time with your Akva University account, okay? But if you did already, then it's great. So the upper part of the ratio is called the, the upper part of the ratio is called numerator. So in Russian, we call this числитель. In Uzbek, we call this surat, right?
Yeah.
And the down part is going to be called as a denominator. In Russian, we call this знаменатель. In Uzbek, we call this as makhraj. Okay, so if you are going to multiply two numbers like A, B, multiply to the CB, can I mute your mics? If you have any questions, you're free to unmute and answer. We simply multiply numerators, these two numerators, and we simply multiply these two denominators, right? But at the same time, if I would like to add two quotients, then there is a constraint, there is a условие, right? That I can add these two quotients if and only if their denominators are the same. Like AB plus CB can be added if B on the denominator of the first ratio is the same as the B on the denominator of the second ratio. Then I can add this. And in this case, I'm just going to simply add two numerators. Okay, let's do a small example. So let's say 2/3 plus 5/3. Then I can simply add them because this constraint is fulfilled, right? So the 2 plus 5 divided to the 3, it's going to be like 7 divided to the 3. But now, if I say what is like 2/3 plus 3/5, how to add these two ratios then? So we can,
okay.
So we cannot add these two ratios because their denominators are different, right? But we've got these two rules, how to add and how to multiply. And if this two denominators, so there is a way how to add these two denominators. We know how to do this if their denominators are the same. But if they're not the same, what we have to do is we need to make them the same, right? This is the key idea of engineers. Like if you've got these two basic rules and you need to make work these rules for all of the other cases as well. Okay. For example, I've got these two ratios, their denominators are not the same. But if I would like to add them, I need to make their denominators the same. And the way how I'm going to do this, I'm going to use the multiplication, right? So the 2 over 3 multiplied as a 5 over 5. If I multiply this, nothing changes because I'm simply multiplying this as a 1, right? Plus 3 divided as a 5, multiplied as a 3 over 3. Now, if I use the first law, I can write this as a 10 divided as a 15, plus the second one is going to be 9 divided as a 15. Now I can add them. It is going to be 19 divided as a 15. I mean, of course, you know this from the school as as giving the common denominator, right? Giving like общий знаменатель from the school. But for us, it's understanding the concept. So by bringing our problem into one or into another law. So again, you've got the ratio of addition of the two ratios. And if I would like to add them, I need to make their denominators the same. And I can do this by just multiplying a certain numbers to the numerators and denominators. Okay. So again, the concept is important. Cool. So all of the real numbers can be represented as a point along the number line. And there is exactly one point corresponding to every single number. So we call this as the point-to-point correspondence. I'm just going to show it here as well. This point-to-point correspondence, it's very important for us. So we're going to talk about this when we learn about the functions and inverse functions. But I would like to one more time emphasize this concept one more time. So for every number, there is a single point. This is what is called point-to-point correspondence. If you understand this, could you please give me a counterexample? Do you understand what does it mean, the counterexample? Example which shows that your law doesn't work. Okay.
Can you repeat again?
Okay, so let's start with the counterexample. Do you understand what does it mean, the counterexample? Oh, by the way, are you learning English? Are you taking some English classes?
Yeah.
Yes.
You know, right? Like in English, if there is a law, there'll be always exceptions.
Yeah.
So
Of course.
the same. So okay, in German language, it's super strange that if there is a law, the number of the cases, number of the exceptions are going to be even more the number of the cases which follow the law. By the way, it's like really strange language. But in mathematics, if there is a law, it should work for 100% of the cases. There should not be any exceptions. Okay. So and something which is called a counterexample, it is an example which shows that your law fails to work. Okay. For example, if I say so negative number plus positive number is always positive. Okay. Here is some statement. There is some law. Can you give me a counterexample which shows that this law doesn't work?
Yes.
It's when a positive is bigger than negative.
Just give me example numbers.
Yes.
Like
-2 plus 3.
yeah.
Minus 2 plus 1, right? Minus 2
Yeah.
plus 1 is going to be -1, right? This doesn't work. You know what I mean? So this is not example. This is counterexample. Counterexample. Do you understand what does it mean, counterexample? Counterexample is example which shows that your statement is not working, is not true. Okay. In mathematics, if you just show just one counterexample to your statement, it is enough to show that your statement is false. Okay. It is different from English. There should not be any exceptions in mathematics. Your law should work always for 100% of the cases. So now, one-to-one correspondence is very important. For every single real number, there is a single point which corresponds on the number line. Okay, this is what is called one-to-one correspondence. So I would like to show you another example of the two sets, which is not one-to-one. So for example, let's say I've got the set of items. For example, the Fanta, Cola, and M&Ms. And I've got another set of prices. Okay, for example, 5,000 sims or 6,000 sims and so on. So what do you think? Whether these two sets make a one-to-one correspondence or not?
No.
No, right? Why? Because one price can correspond to the two items from the first set. Okay.
Yeah.
Then this is going to correspond to this this one, for example. And these two sets are not going to make the one-to-one correspondence. So numbers and points make the one-to-one correspondence, because for every single item from the set of numbers, there is always a single item from the set of points. Okay, this is one-to-one correspondence. Do you understand what does it mean, one-to-one correspondence?
Yeah.
It's
Yes,
important.
clear.
Whenever we discuss about the inverse functions, we will come back to this. It's important. So we just talk about the law of the signs, and we say that, hey, so if I add negative plus positive, it can be positive or it can be negative. I don't know. But I can definitely know if I multiply two positives or two negatives are going to be positive number always. So again, if A and B are going to have the same sign, either both of them are positive or both of them are negative, then their multiplication is always going to be positive. And conversely, if you've got the two numbers with the opposite signs, like plus and minus or minus and plus, then their multiplication or their division is always a negative. Okay, so let's try to do a small exercise. So let's say you've got like x is positive and y is negative. Then what is going to be the sign of this number?
Answer will be indeed negative.
So opposite signs, it means that this number is going to be a negative, right? This number is also going to be negative. Negative plus negative is negative. Okay.
Yeah.
So if I say what is going to be x plus xy, what kind of number is it? Is it positive?
Yeah.
Or negative? X
Negative.
plus xy. Could you
Negative.
please
think
raise your
both of
hand?
them.
It is negative.
Who thinks that it is negative?
Negative.
And
Negative. Who thinks that it is positive?
I think it's both of them.
Both of them. Okay.
Yes.
Yeah.
Again, in mathematics, we can't really say that it both of them. We usually say that not defined. Not defined. Okay, because we don't know. It depends, right? So it depends on the values of the x and y. So it can be positive sometimes, it can be negative sometimes, right? Because plus, so if I add one positive number to the negative number, it can be either positive, either negative. So that is why we should. Yeah, thank you. So it depends on numbers, yeah. So whenever it depends on the numbers, whenever we don't know this for sure, we just say that it is not defined, okay? The same as like, you probably know that division on the zero was not possible in the school, but I need to tell you, I need to open you a secret that it is possible actually. You can divide, for example, 3 to the 0, and this is going to be equal to the infinity, okay?
Yeah.
But 0 to the 0 is not defined. Okay.
Yeah.
And it's not defined. It doesn't mean that it doesn't exist. It basically means that, well, it depends. Okay. So sometimes it can be a finite number. Sometimes it can be infinite number. We're going to discuss about this later on. I think mostly about the calculus course, of course. But again, not defined in mathematics doesn't mean that you don't know how to do this. It means that it depends. Okay. Cool. So also the non-strict inequalities, it means that like more or equal or less or equal. Okay, so both of them can be true. So let's try to compare those numbers together. So for example, if I compare 2 and square root of 2, which one is greater? Which kind of sign I need to put?
2.
2 is greater, definitely.
2 is greater. Yeah.
2 is bigger.
Because square root of 2 is 1.41 or something like that. Okay. What is saying? Which is greater, pi or
Pi.
3.14?
Pi.
Pi.
Isn't there
Pi.
equal?
No. They are infinite.
Pi is
No.
greater.
It's pi
It's fine. Yeah.
because
Are you
it is
sure?
a real number.
Oh, 3.14 is also a real number.
Yeah, but after pi, there are so many numbers, and in the 3.14,
Okay,
it's
you're
exact.
right. You're right. Pi is greater because if you compare 3.14 and 3.14 and 15, for example, this number is going to be greater. Okay. Could you please try to explain me from the computer's perspective how you would do this? Because you know that you probably most of you probably don't know about the computer precision and this kind of things in the computer, and you will get to know all of these things later on. How you would do this in a computer, how you would compare these two numbers in a computer.
With such equalities.
If you don't have. Oh, okay. So for example, if you would just like take the difference, and if the difference is not 0, right? It means that one of the numbers are greater. For example, pi is going to be greater. Okay, so we'll talk about this computer precision things also later on. So 1 over 3 and 0.33333. Which one is greater?
First one, 2 0.
1 over 3.
1 over 3.
1 over 3.
What if I will put like 3 more 3 here?
It doesn't
1
matter.
over 3.
Again,
What about like 2 more? It doesn't matter.
1 over
Right?
3.
It's still going to be
Yes.
1 over 3 is greater, okay? Because 1 over 3, it's like 0.333 with infinitely many 3s. So it doesn't matter how many 3s you're going to put here. This number is always going to have even more 3s than yours, right? So that is why it is going to be slightly greater. What about a squared and 0?
We don't know.
Well, actually, we know. A squared.
A maybe
A square.
give 0.
it depends.
So that is why I can do this with greater. Yeah, greater or
From any
equal.
number.
Yeah. If a is a real number, then a in a square is going to be greater than or greater or equal to the 0, right? Because now it depends. So do you remember, do you see that whenever you're going to compare two numbers, like real numbers, you can always use like strictly greater or equality sign. But whenever you're comparing a variable, a square is a variable with a real number, now you can use the like this non-strict inequalities as well. And in this case, it's going to be greater or equal to the 0, because it is possible that if a is equal to the 0, then they are equal. And if a is any other number, for example, -3, then a in the square is going to be greater than 0. Okay. So non-equality means that it is possible that it is like non-strict means that it is possible that it can be equal or
Апомет гэр кипкенен кем бар арaya gitti. Erteyen kızak en çarşamba kemiz geri gitedi.
yeah. So better to mute because I'm going to put this to YouTube. Mute koyun to Sherzad. Microphone.
You will get a lot of views.
Yeah. Okay. So there is absolute value thing as well. So the absolute value is whenever we're simply going to take the value of the number without taking into account its sign. For example, the absolute value of the -3, it's going to be simply 3, or the absolute value of the 2, it's going to be simply 2, and so on. So let's do a couple of exercises. So 3, absolute value of the 3 is 3. Absolute value of the -3 is 3. What is the absolute value of the square root of 2 and -2?
That's positive.
Sorry.
Give
It will be positive.
Yeah. So
0.539.
I think it's
2
2
minus square root.
minus.
Yeah.
Yeah.
2 minus square root. Right? The same is like if I say, what is the pi minus 4? Pi minus 4, and its absolute value, it's going to be 4 minus
4
pi.
minus 4.
Because it's going to be a positive part of the number, right? So what do you think? I mean, absolute. Did you ever had an impression that, okay, the absolute value is kind of easy, right? I mean, from the school, it was always learned like,
Yeah.
hey, there is an absolute value function. So whenever you've got just a number, just take it positive part. Whenever it's negative, just take it positive part. And I always thought like, hey, it's too easy. So why I need this? Did you have this impression? Like why we
Yeah,
need
yeah.
the absolute value? Okay, so the absolute value can be used in many different things. For example, when the value is important and the direction is not important. Can you give me something which you would measure where the value of this measurement would be important, but direction is not? Can you give me an example from your life? Value is important, direction is not important. It doesn't matter in which direction you're measuring this. Value is important. What do you think?
For example, distance.
For example, distance, right? Okay, great. So let's say I've got a person and you are staying here. And if you would like to calculate the distance from this A point to the B point, what you can do is you can just put the steps, or you can put the steps to go to the C point as well, right? It doesn't matter in which direction you move, either to the forward, either to the backward. The number of the steps is your distance, right? It doesn't matter in which direction you go. For such a cases, using the absolute value is really handy. So we can use the absolute value by building a beautiful mathematical structure on the top of this. So in general, we say that, hey, the distance between 2 points A and B is simply going to be the difference of their coordinates. And it doesn't matter which one is coming first and second, because I'm just going to take the absolute value, okay? And there are many different other cases when we're going to use the absolute value, and I'm going to show it with you overall this course, but the easiest and the main example of the absolute value is the distance, okay? So let's say I would like to find a distance between 2 points, -3 and -5. What is the distance?
Yeah.
2, right? It's going to be -3 minus -5. So these two minuses are going to give me plus, right? It's going to be -3 plus 5. It's going to be 2. So what is the distance between -3 and 1?
4.
I'm going to do this -3 minus 1. It's going to be -4. But again, so I don't need this sign minus, right, for measuring the distance, because the number of the steps is more important for me. So that is why I'm going to take its absolute value, and this is going to be equal to the 4. What is the distance between -5 and 6?
11.
11, right? Again, I'm going to take its absolute value. Okay, well, absolute value is very easy operation. You just take its value, but in essence, it's very important. So especially in mathematics, there are not so many cases when we use the absolute value, but for example, in chemistry or in physics, there are so many important applications of the absolute value, where, for example, when you're going to measure the current, for example, the absolute value is important rather than the sign, for example, sometimes, okay? So plus or minus and so on, okay?
Yeah.
Okay.
So let's talk about the exponential numbers. So they are one of the really important numbers, but at the same time, they are really easy to work with them. So I'm explaining you what does it mean in a moment. So if you've got a positive integer n, especially, so essentially, if you're multiplying 5 to itself 129 times, it takes a huge space and time to write 5 129 times, right? So in nation, they figure out, hey, so why we should just write 5 129 times? Isn't it better for us to just say that 5 is already written 129 times in this way? And then they became with an idea of exponential numbers. We call this number as an exponential number, where this base or this bottom part is going to be called as a base, And the upper part is going to be called as exponent. Exponent. So far, we are going to just restrict that n, this exponent, is going to be as an integer. Do you remember how we denote the integers? Whole numbers?
Yeah.
How?
Z.
Z, great. So the n is going to be from the z, okay? And a is going to be from the set of real numbers. A is going to be from the set of real numbers. Okay, so instead of just writing 5 to 129 times, I could just write down 5 in the power of 129 in order to denote the exponential number. So there are a couple of operations with the exponential numbers, but before we do this, let's try to do some exercising. So what is going to be 5 in the power of 3?
125.
25.
Okay, so in order to do this, I need to multiply 5, 5, and 5. It's going to be 125. What about 1 over 2 in the power of 3?
1,
2,
2, 2, and
8.
plus 8.
1 over
Or 8.
8.
Okay, 1 over 8. What about minus 3 in the power of cube? 3.
Minus 8.
Minus
8.
8.
Okay, I can do this minus 2 times to the minus 2 times to the minus 2, which is going to be minus 8. What about minus 3 to the power of 4?
Minus 20.
Minus
Not the
8
minus,
to
not
the
minus.
1.
Okay, it is different.
81. 81.
81.
Minus
Minus 21.
Minus 1 times to the 3 in the power of 4. Okay, so this is different than minus 3 in the power of 4. Okay, so minus 3 in the power of 4, it's going to be minus 81. And minus 3 in the power of 4 is going to be plus 81. So I know that it sounds weird when you just hear without seeing this, but this is just a difference in notations. Whenever you write down minus 3 in the power of 4 without the brackets, you need to understand this. You need to first of all power this 3 to the 4 and then multiply this as a minus 1. Okay. Okay, so there are a couple of operations with them. And the main one is if you multiply a in the power of n to the a in the power of m. So I hope that you still remember this, but let me just illustrate this. A in the power of n means that I need to multiply a to itself n times, and a in the power of m means that I need to multiply a to itself m times. But altogether, I'm multiplying them n plus n times, right? For example, if you are going to power up a to the 3 and multiply this to the power of the a to the 4, it means that you write down a 3 times, then you write down a 4 times, but it is obvious that you're writing down a 7 times altogether, right? So that is why a in the power of n times is a in the power of m. If the bases are the same, it is going to be nothing else as a in the power of n plus m. So at the same time, there's another formula. It's powering up a into the m. So a in the power of 2 and the power of 3 is not going to be just a submission. It's not going to be the addition of this 2 and 3. It's going to be the multiplication of the 2 and 3. It's going to be a in the power of 2 times the 3, which is going to be a in the power of 6. And again, the idea is, so you're going to just look to this a in the square. It's just the one number. Not just one, it's just one symbol. I'm just going to mute. So again, one more time, I would like to ask you to just mute yourself. If you're not talking, just unmute whenever you talk, it's okay. So a in a square, it's going to be a in a square times a in a square times a in a square because you're cubing this up, right? So it means that it's going to be then a in the power of 2 plus 2 plus 2, which is going to be a in the power of 6. Okay. So let's do an exercise. What is going to be 5 in the power of 3 times the 5 in the power of 4?
Power of 12.
5 to the power 9.
3 plus 4. It's going to be 7.
7.
Right?
7.
Yeah.
I need to add. What about minus 2 in the power of 3 in the power of 2?
Power of 6.
3, 4.
It's 2 in the power of 6,
2
right?
Yeah.
to the power of 6.
It's simply 2 in the power of 6. Why not minus 2 in the power of 6?
Because it is
Suppose
2.
Could be a positive number, right?
Yeah.
Okay. So, and actually, so again, you can write this as minus 2 in the power of 3 times the minus 2 in the power of 3. It's going to be 2 in the power of 6. Okay. 2 in the power of 2 multiplied to the 3, but you need to always keep in mind about the sign as well. Okay. These two important laws are really important, and they're going to be the basis of bringing us a new formula, which enables us to find the negative powers of the numbers. And in order to do this, we are going to introduce with a new notation of reciprocal. Could you please write this down? It's very important notation, which is kind of very, there is no such a word in Uzbek or in Russian, reciprocal, which is in English. So reciprocal of a number is just the inverse of a number, okay? So for example, if I say, what is the reciprocal of the 2? You say me what?
1 over 2.
1 over 2. What is the reciprocal of the 5?
1 over 5.
1 over
Okay.
5.
What is the reciprocal of minus 1 over 3?
3.
3.
3, right? What is the reciprocal of minus 3? Plus 3.
Minus
One-
minus 1
Minus 1 over 3.
over 3.
Minus 1 over 3, right? So we just take it 1 over this number in order to find its reciprocal, right? So let's find the reciprocal of minus 4. Reciprocal of the 4 is
1 over 4.
1 over 4.
1 over
1
4.
over 4.
So what is going to be the negative power of the 5? So negative power 3 of the 5.
1 over
3 over 5.
125.
Yeah, but again, so actually, I mean, of course it might be obvious for you, but for me, it is important is how you are doing this using the laws which we have already, right? For example, you're combining this law with this one, right? You can write as 5 in the power of minus 3 as 5 in the power of minus 1 in the power of 3, right? Then you can just multiply their powers. Minus 1 times the 3 is going to give you simply minus 3. And we know that 5 in the power of minus 1 is the reciprocal of the 5 in the power of 3. Now it's going to be 1 divided to the 125, okay? Which brings us to the new law that 5 in the power of minus 3 is just nothing else as a 1 divided to the 5 in the power of 3, right? Or in general, a in the power of minus n is equal to the 1 divided to the a in the power of n. Okay, it's very important formula. Okay, so that is why just using this formula, I can calculate this power. For example, 3 in the power of 5 divided to the 3 in the power of 2 can be written as a 3 in the power of 5 times this 3 in the power of minus 2, right? This number on the denominator can be put on the numerator by just making its power opposite sign of the sign, right? And now just using this
3
law, I can just
power 3.
3 in the power of 3. Great, thank you. 27. 27. Okay, so this is again important 3 laws, and you can build the new laws on the top of them in order to bring the new ones. So let's do a small example. So I need to simplify this term. Okay, in order to do this, I would like to expand all of the brackets by applying the exponents to all of the variables. So there are like the variables like R, S, and I'm just going to apply the powers to all of them. So what is going to be 2 in the power of 2?
4.
4.
R in the power of 3 in the power of 2.
Or 6.
R power 6.
What about S in the denominator in the
A
power of 2?
squared.
S equation.
Squared.
If I write this on the numerator.
Minus 2.
S to the
And
power
minus-
minus 2.
Okay, so do you understand this? Because S was in the down, I just put this on the top, so that is why S in the power of minus 2. Multiply to S3. What is this?
S
S3.
cubed.
S3.
S cubed.
What is R cube in a cube?
Power
Around
Minus 9.
minus 9.
Negative 9.
Okay, cool. Now I'm just going to add up the numbers. It's going to be 4 times R in the power of 6 plus, minus 9 times S in the power of minus 2 plus 3. It's going to be 4S divided as R cube. Right?
Yeah.
Yes.
Yeah.
Super easy. Actually, exponentials are not so difficult. You just need to know the 3 laws. And my main concern about like freshman students is knowing this negative power, how to handle this, how to calculate this. And it is easy. You can calculate this like a in the power of n and take its reciprocal. Okay. Reciprocal is a new word. You just need to learn reciprocal. Okay. It's a very important word. We're going to use this a lot. Okay, so the exponents are not so difficult, but which is more difficult is the radicals or the nth root of a number. So the nth root of a number a is such a number
Rakam
b.
nerede?
Okay. Mute qilib qo'yinglar iltimos mikrofonlaringizni. Qachon gapirish kerak bo'lsa unmute qilasiz. Nth root of the a is such a number b, so that a b in the power of n is going to give you a. So let's do a couple of exercises. So what is going to be the square root of 16?
4.
4.
4.
Why? Because
4 equation
4 in
it
the
is
power of
16.
2 is equal to the 16, right? So
Yeah.
whenever we have 2 on the root, we just simply don't write this because, I mean, it's obvious, right? So what is the cubic root of the 8? Minus 8, sorry.
Minus
Uh,
2.
-2.
Minus
Minus
2.
2. Why? Because minus 2 in the
Minus 2.
cube is equal to the minus 8, right?
Yeah.
What about minus 16's fourth?
Mine,
Minus-
no, it's not.
2.
Not
Or there is no
Not
real
defined.
number, right? No real number. Okay. I would like to talk a little bit with you about the inverses. Okay. So the radicals is, in terms of the operation, is the inverse operation. So let me write this down one more time. The expression, this kind of expression is going to be called the radical. It doesn't matter what is the nth root. For example, the square root of 5 or cubic root of 9 and so on. All of them are going to be called as a radical. So whenever you've got the root, this is going to be called as a radical. The number which is inside the root, it's going to be called as a radicand, and the sign is going to be called as the radical sign. Okay. If I just say here, what is the 2 in the power of 3, you can easily tell me that it's going to be 8. And you know this, how to do this, right? I mean, there is this trick algorithm how to do this. You multiply 2 in order to get to 8. But if I say, hey, what is the fourth root of 16? What is this?
2.
1, 2.
2.
How do you know? How did you figure this out?
Because
By multiplying 4, 2.
I'm not asking why it is 2. I'm asking how did you figure this out? Do you understand the question? Man nimaga ikkiligini so'ramayapman. Qanaqa qilib ikkini topdingiz so'rab.
Model bo'lishi ham mumkin.
Let us to
Minusli
draw
bo'lishi ham mumkin.
blackboard.
Yeah, I mean, so if you're taking fourth root from the 16, it's simply going to be 2. I mean, the answer is correct. I'm not again asking why it is 2. I mean, it is 2, true. I'm asking you, how did you figure this out? Figure out догадаться. So, как вы догадались, что это 2?
Let us draw in the blackboard. Okay.
No, I mean, can you tell me? Can you express like your feelings? For example, if I say you like find the square root of 81, you say this is 9.
9.
How did you figure this out?
Because we know
9
that
squared
Because you know this.
square
one.
root is equal.
yeah.
Okay,
Eight.
because you had an experience, right? So you see that this is the inverse problem. So 9 in the square is equal to 81. It's a forward problem, okay? So you know how to reach a certain point. But now when you find yourself on one of the point, how to go back? This is the inverse problem, okay? Solving inverse problem is always more difficult than solving the forward problem. Okay, so and in order to solve such inverse problems, of course, we need to be really experienced analytically. Okay, or we need to figure out some algorithms or engineering techniques how to solve this kind of engineering problems. So you probably know that you can just take any calculator and type, for example, 2.3172. Do you know how your calculator finds the square root of this number?
No.
Or maybe it does in this way, like it takes, like, for example, if I say, hey, what is the square root of 15? How you would do this?
Having form.
I mean,
On the root.
Multiplied by 4.
huh?
3 multiplied by 4. No.
No.
Sorry.
If it would be 16, that you would tell, hey, it's 4, right? I know that this number is between 3 and 4. And what I can do is I can say, hey, maybe this is going to be roughly 3.8, right? And then I multiply 3.8 to 3.8 and see how close I'm to the 15. If not, then I'm just going to increase this, like I'm taking like 3.85. Then I'm going to multiply this to itself and see how close I'm to the 15 and so on, right? In this way, you can roughly know what is going to be this number, but this is going to be very like kolkhozny or method, right?
Yeah.
So I hope that computers or calculators don't work in this way. So they figure out an intelligent algorithm how to take the square roots, okay? But at this point, I just wanted to say you that finding the square root or cubic root or any root of a number, it's an inverse problem. It's not a forward problem. And there is no single way how to do this. You need to be really experienced. You need to do all of these exercises a lot in order to be able to solve the inverse problems. So that is why, like, it's important for mathematicians to do a lot of exercises. Okay, I mean, so you know that, for example, square root of 81 is 9 because you multiply 9 to itself many times. So that is why you simply figure this out. Okay, but if I say, hey, what is going to be 243 from the square root? I mean, you probably can figure this out, but it's difficult, right? Because you probably didn't do a lot of exercises on this. So my advice is to do a lot of exercises so that you can handle with the inverse problems. And again, the square root is the inverse problem, and it is one of the biggest challenges for engineers. So overall your career as an engineer, you need to always try to solve the inverse problems. Okay, so at some point I will teach you some algorithms how to take the square root. Okay, but we need the derivatives. Okay, so when we will learn about derivatives, we will come back to this algorithm and I will show it to you. Okay.
Yeah.
Cool. So there are a couple of things I need to mention here that so some of you told me that whenever we take the square root, we need to take the module, right? So, well, you take the module if the number under the square root is a negative number, right? For example, if I say what is going to be -3 in this -3 in the square, taking from the square root, you can't really just write this as the -3, right? Because this number should be a positive number. So that is why you take its module and you write this as a 3. So this is where this low is coming from. So I think it's like we are approaching the most important part. Sorry, I will take a couple of more minutes. So so I need to mention that radicals are so much connected with the exponentials. First of all, they're kind of inverse of the exponentials, of the idea of the exponential. And at the secondly, I can express the radicals as the exponential numbers as well. For example, instead of just writing down square root of 2 I can write 2 in the power of 1 over 2. Whenever I write down a power of numbers using the rational numbers, they can be written as the radicals. Okay, for example, if I write as 5 in the power of 1 over 4, means that this is the 4th root of the 5. Okay, and I would always suggest you to use the exponential notation for the radicals so that all of the laws which we have learned so far, like a multiplication of the 2 radicals or powering up the radicals, are going to be applied to the roots as well. For example, if I say what is going to be 3 in the power from the 3rd root, taking from the 5th root. you are going to use the exponential form of those numbers. So the 3 from the third root, it's going to be 3 in the power of 1 over 3, right? And then you need to take the 5th root of this, 1 over 5. Then you're going to just multiply this. It's going to be 3 in the power of 1 over 15, or this is going to be 3 from the 15th root.
Great.
Okay, do you understand this? So this
Yeah.
is,
Yes.
okay. Exponentials are easy, but there are 2 things you need to keep in your mind. The first thing is like 2 in the power of minus, a in the power of minus n. It is nothing else as 1 divided to a in the power of n. This is the first thing which you need to keep in mind. And the second is nth root of the a is equal to the a in the power of 1 divided to the n. Okay, this is what is called the radicals. And these 2, I think, equations will help, are the key equations which enables to solve many problems connected with the exponential numbers. So please note that I'm just calling this exponential numbers intentionally, because later on we're going to learn about exponential functions when we are going to just simply expand the domain for the base, for the exponent. Okay, so let's finish for today. I hope that it was okay. So again, so you see, so during the lectures, we're learning about like many basic things, but I hope that you're learning many new things at the same time, like looking to the same thing, which we knew from the school, for example, from the different perspectives. Okay, this is our goal. Okay, cool. Thank you very much. Then see you
Thank
next
you.
time.